All right. What I've been working on, it's not just gravity. It's universal laws for gravitational systems. And what do I mean by that? What's the difference, right? So a universal law has to be universal. It means it scales to every size, it repeats everywhere. It's universal. And I've come across a few universal laws in the process of this. And but that means that gravity has to scale to every size, galactic down to atomic, and smaller and bigger. Um, Having a tough time. I've gotten there. I've gotten there. I've made a lot of changes along the way. A lot of changes along the way. Where I'm at right now is I went through my system. I had a paper written up, and before I sent it, I says, "All right, let me look at it from a few other angles." So I went looking at it and looking at it, and I even went back to Einstein and everything with the warp geodesics and all that. And it doesn't work. It doesn't work. It really doesn't. Um, what does work is actually a cumulative static charge. So, what do I mean by cumulative static charge? Um, it's magnetics is a moving electric charge that is moving, and it creates a magnetic field, and that magnetic field is strong, um, and that's what holds atoms together. It's what makes magnets work, stuff like that. And then you have a static charge. A static charge is very weak compared to a magnet, and it's got to be kind of like suspended and just kind of separate. It's not a magnetic charge. It is, but it's not. I don't know how to explain it. It's very weak, but it works on everything. And so uh, all the atoms are neutral because their magnetic charge is locked, but they are still particles, and they all carry a charge. And you are made out of particles that carry a charge. They're all neutral, sort of, because they're all system locked. But wherever there's a universal law for you. Wherever there's a charge, there's mass, which means wherever there's mass, there's a charge, and that charge we see as gravity. But to get that big mass, it starts off with charged particles. So you got to get your atoms together first and everything. So your charged particles might form plasma, but the plasma ain't gonna do nothing until it's cooled off, right? But when it cools off, it can be a gargantuan cloud, and the static is equal pretty much throughout all of it, except for the edge, which is where time dilation comes in. So time dilation gets the whole thing working as a system through time dilation. It starts spinning it and pulling it in. And as it spins it and pulls it in, you end up with more of a ball and more of a ball, and eventually the center gets spinning. When the core gets spinning, it starts spinning on the outside. When the core gets spinning, it gets dense real fast. And as soon as you got that density, things speed up pretty quick. um, and I says, time dilation doesn't work for that. I says, you get the added time dilation, but it's not really gonna work like that pull. Like when you're standing there on Earth or sitting in my chair, I feel that pull. And if I was in space, like Einstein says, and you fall, you're going to fall, and you won't feel like you're falling. And you're going to keep accelerating. So your geodesics are right out. The Einstein warping space, that's out because the thing pulling you, you would feel like you're being pulled. And then when you get to a certain speed, you're going to feel like you're being pushed back. And that's not what would happen. So what you end up with is really the only thing left is that big planet that has a static charge. And it works as a pull. But it's got to get created first and all that other stuff. And the whole thing, everything, works in systems. So if you look at the solar system, you have a gargantuan magnetic charge and gravity and all that other stuff and whatever you want to call it, and you got radiation coming out, okay? And you got frame dragging, and it's frame dragging the magnetic field that it's using. And time dilation sets the entire solar system. And that's why the solar system is kind of separated from everything else around it. And it creates our little shield, our little bubble, right? There's not a whole lot of frame dragging though with our solar system because our sun's moving very slow, right? And our system's pretty solid. It's not really adjusting or changing much. It's nothing like that. So the whole system is really pretty set. Saturn and what's the other big one? Oh man, I'm tired. It's been a while. Saturn and Jupiter get too close every once in a while, throw themselves off of their alignment, out of their orbit, and you'll see them wobble, and they'll just wobble, 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 and wobble, and then wobble themselves right back into place and directly back into their orbit and go right back under their smooth, regular orbit. And it threw scientists off for a little bit. And end result is we are frame dragging in a big circle. The whole system is frame dragging around the sun, and time dilation controls the timing. And then, of course, you get, what we call regular gravity. And that's actually more of a static pull with a weak radioactive push, right? That's all your radiation coming out and stuff. And what happens is when they get out of alignment, anytime you're not in the proper frequency, you start dealing with time dilation, which is a resistance to velocity. And we feel it just sitting here, but that's what holds the planet together. What holds the planet in orbit, on the other hand? Well, if it gets out of alignment, just a little bit, if it gets out of alignment, it literally gets pushed back into place. Anything that's going to throw us off of alignment is going to be like a catastrophic event. We're not going to be around to worry about it afterwards anyhow. Now, when you look at a galactic scale is a disaster because the core, it's not as simple as a nice, slowly moving sun. It is a cluster, gargantuan cluster of a whole bunch of mass and different stars and black holes and just madness in there, right? And it's eating. It's literally devouring galactic dust and stars and all that other stuff. And when it eats, the core slows down. What do I mean by that? The spin. All right, the rotation of the core slows down because it gathers mass. When it's gathering mass, it slows down. And when it does that, the surrounding core tries to flow straight in because it no longer has that frame dragging going around like it was. So when the frame dragging works on atomic scales, everybody knows it as the weak push or the strong push. What that is frame dragging. So when you get close to the core starts ripping you around in a circle rather than just letting you fall straight in. It's the control measure. So when you look at an atom, why doesn't the electron always bang into the proton? Because everything's frame dragging at an astronomical rate. If you look at the spin of these things, it's insane. On a galactic scale, it's still pretty big, but it's not like inside of an atom. The atom works the way it does because of frame dragging, because of time dilation, because of the magnetic pull, the absolute spin and orbit. It's insane levels, okay? And that's where Schrodinger, when he originally made the math, that's what he made the math for, was an electron has very little mass, right? So it's not spinning like a top very fast. So it makes up for that because it has to keep its +1 charge. So it makes up for that with orbital. All right, so it's very small. It has very little spin, and it makes up for that +1 by doing the orbits. And because a moving charge gains a lot of charge, it gains a lot of magnetic pull, right? Whereas a stationary charge, a spinning, builds more of a static charge. So the proton is very, very heavy, has a lot of spin, angular spin, angular momentum, but not a whole lot of orbital. So what happens is when the proton gets too close to when the electron gets too close to the proton, the Frame dragging actually helps pull it away. Just rips it away. Says, get back out there. And gives it actually some angular spin, momentum spin to get out there and then go back into its higher orbitals. The way electrons drop in frequency, they get out of the time dilation lets them know that they're in the wrong spot. All right, they're out of timing, and just kind of like Saturn, it'll just make it wobble. It'll cause resistance for being in the wrong place, and when it does that on an atomic scale, it creates the light waves and then drops frequency, and gets it back into its spot, into its orbit, which is basically the same thing that happens in a galaxy. So when a core is spinning too fast, right, it's losing grip on the rest of its timing, and it's losing grip basically on its food source, right? It starts going too fast, and it starts ripping everything around in circles, and as it catches up, it tries to fall in. But if it's going too fast, it's not going to catch up, right? So you end up with for the core of a galaxy, for it to release its spin, when its angular momentum goes too fast, it starts jetting material. Even out of black holes, it'll jet, release all that extra energy, and slow down its angular momentum. And this allows it to keep in time with its disk. But galaxies, 150, 200,000 years wide, from the core. And what happens is, if the core is going fast, you won't know about it for 150,000 years. And then you still have to adjust, which is on a galactic scale. It means you change your orbit to stay in time. But that takes time, and it's 150 light years away, so it takes a little while. It looks a little different in a galaxy, I'll tell you what, than a solar system. Like, we're 8 minutes away from the sun. If the sun disappears tomorrow, we'll know about it 8 minutes afterwards. If the entire core of our galaxy disappears, we won't know about it for 50,000, 100,000 years from now. It's crazy. But anyways, so when I always talk about inside of an atom, things move so fast in such a tiny little spot that the electron stops acting like an electron, but it's still an electron. It just stops acting like one because it's moving at insane speeds. So the universe sees frequency, okay? It's seen as a frequency. And when time dilation comes into effect, it's talking about frequency reduction, okay? And that's resistance to, velocity. And velocity is resistance to the EM field. And we have frame dragging. So to be resistant to the EM field means you're going against the flow of the system. You're not in time. Now, when you're in gravity, gravity is considered acceleration. That static pull from the entire planet having a static charge is pulling everything to it. And that pull we feel as velocity, which gives us our time dilation. Anyways, I'm working on that math, guys. It's going to take me a little while. That is some complicated stuff, but we're going to get the galactic spin in there. Don't worry about it.